Morning, everybody. We're going to look at the unit for measurement today. It's a pretty short unit. It's pretty intuitive, and we're mainly going over it because it pertains a lot to how the IB exam expects their answers to be delivered. And so the way that they do this for the IB exam is they use something that's called significant figures. And so you may have seen this in a science class, but we are going to go over it just to hash over that expectation. And so when we use the word significant figure, that's referring to the significant figure of a decimal number is the first or the furthest leftmost non-zero digit. So if we were looking at two numbers here, the first one here is 4,567. We'd go to the furthest left of this number and say, okay, is that a zero, yay or nay? If it's a nay, that's our first sig fig. 5 would be our second, 6 would be our third, 4th would be our seventh, or 7th would be our 4th, excuse me. So then right here, the first sig fig of 0.01234, 0 doesn't count, 0 doesn't count. The first sig fig here would be 1, and then 2 would be the second, 3 would be the third, 4 would be the fourth, so on and so forth. And so when we're talking about sig figs, every digit to the right of the first sig fig is regarded as another sig fig. So just kind of what we were talking about there, first, second, third, fourth. And the rules for rounding sig figs are the same. They are always the same in that when you round up a sig fig, you're going to look at the number directly after. If it is 5 or greater, you'll round up. If it is 4 or lower, you will keep it where it is. And when you're taking an IB exam, IB expects you to round to 3 sig figs. That is super crucial. So most of the rounding that we're going to do today and the 3 examples here, IB expects 3 sig figs. I would write that down somewhere. So we're going to practice doing that a little bit. So the first thing that we're going to do here, we're going to round to 3 sig figs. So real quick, pause the video and label the first sig fig of each of these numbers. So it shouldn't be too bad. So pause that. So the first one here, the first sig fig here is going to be 7. So we're going to go out to 0 and then 4. And because the number right after that 4 is a 6, we're going to round this up to 0.0705. We're going to round that up to 0.0705 because whenever you're doing sig figs, you're going to list those 3, and then whatever the number is, that's going to determine whether you round up or down. Now on this next one, we go 1, 2, 3, and then we're going to look at that number before that. We're going to say 101, and because this is a 4, we're not going to round up. We're going to round down, so this is just going to be 10,100. 10,100. We're going to keep where we look at these 3 numbers, and if what's next behind that isn't greater than 5, we're going to round that down to 0 instead of rounding it up. And then the last one here, we've got 2,498. So our first 3 sig figs are right there. We're going to say 1, 2, 3. So this is where we're going to round to. So since that 8 right there is above 5, we're going to round this up to an even 2,500. And if you're looking at that and you're like, wait a second, Mr. Price, I need some more examples. Trust me, we will get a couple more. We will get a couple more. So the next thing that we're going to look at here is we're going to look at approximation. And more specifically, we're going to look at the mathematical definition of approximating. And so a pretty quick way to estimate a calculation is to do what's called a one-figure approximation. And basically what that means is we're just going to round to 1 sig fig. We're going to round each number to 1 sig fig and then perform the calculation. So if a number's higher, we'll round it up. If a number's lower, we'll round it down, and then we'll see where we end up. So for example, if we round both of these things, so 8's the sig fig here, 5's the sig fig here. If I round this up, so the number before this is a 7, so 872, if we're doing one sig fig, is going to round up to 900. Now 52 here is going to round down. So this is going to be the same thing as 900 times 50. And the reason we're approximating, that's going to be 9 times 5, but we're going to throw 3 zeros on the end of that thing. So we're going to say that's going to be 9 times 5 is 45. And we're going to say 0, 0, 0. This is our approximation for this. And if you look, if we do 872 times 52, we're pretty close into the ballpark of that. Like if we were just trying to estimate that real quick, this is a calculation that we could probably make in our heads. So we're going to do a couple more of these. So let's see. If we do 61,108 or 61,812 divided by 384, we're going to round these to one sig fig. So since the number before this is a 1, we're going to round down to 0. So we're going to call this 60,000 divided by, so let's see, 384. The number after the 3 is an 8, so we're going to round up to an even 400. And I don't know if you all know this, but when you're dividing things with zeros, these are just assumed tens places. To make this easier, you can actually cross out a couple of these zeros. So now this is just the same thing as 600 divided by 4, which we can figure out more easily. We can usually approximate it without a calculator. So that's going to be 150 there, 150. So we're going to try one more approximation. So I want you all to pause this and try approximating this on your own for me real quick. Try approximating it on your own. So let's see, we're going to round 4, and 0 is not the sig fig, 4 is right here. So we're going to say 4 is going to round down, so 4 times, this is going to round up to 0.5. So we're multiplying 4 by 1/2, or 0.5. That's going to approximately give us 2. And again, that's just serving as a quick way to approximate those numbers. Just a quick way to approximate. And so we're going to move on, excuse me, so that was 2 sections pretty quick. Just using sig figs and then using sig figs to approximate numbers. This is a pretty swift unit. And so what we're going to talk about now is some errors that people can make in measurement. And so whenever you take measurements, you're usually reading some sort of scale, whether it's a ruler, whether it is a scale for weight. There are units that you can use to tell those. So scales, so like for example, on a ruler, there's usually, it has centimeters marked on it. But when you measure the length of an object, it's very, very rare that it's an exact length. And so what we as humans do is we approximate the length by recording the value to the nearest centimeter or to the nearest inch or to the nearest whatever unit there is. Now the issue with doing so is that your answer could possibly be inaccurate by up to half of whatever unit that you're rounding by. It could be inaccurate to half of the smallest division on your scale. So you could overestimate by 1/2 or you could underestimate by 1/2. And so we're going to look at a couple of examples with this. So if, for example, we were using a ruler to measure the length. So again, this is example 5 on page 23. We are in the orange book. Apologize about that. I should mention that earlier. So if we're using a ruler to measure the length of her pencil case, and she records the length as 18.7. We want to know, okay, what possible values could there possibly be here? Now, on a ruler with centimeters, there are usually millimeters. So we need to first acknowledge that. So the smallest unit, if we're using length here, 18.7 centimeters is equal to 187 millimeters. Now, if we are measuring in millimeters, that's the smallest unit on our scale here, the measurement error that we could make is plus or minus a half of a millimeter. So what we're going to have to do is we're going to say 187 here plus or minus 1/2 of a millimeter. And this is the range of error that we could possibly make here. And so what that means is, so 187 minus a half, it could be 186.5 millimeters. The length could be between that, and it could go all the way up to 187.5 millimeters. And if we were talking in centimeters, if we wanted to refer to that, because that's what we started in, we'd say 18.65 centimeters is less than or equal to, the length is less than or equal to 18.75 centimeters. Either one of these would work. Either one of those would work. And so whenever you're recording measurement error, it can compound depending on what you were trying to find. So, for example here, if you were doing a rectangular board that was measured, so if it was measured 78 by 24, so we're going to call this short side 74 centimeters. We're going to call this tall side 78 centimeters. We want to list the error, the possible error that could occur by listing the smallest perimeter that could be measured and the tallest perimeter that could be measured. So as a reminder to you all, you get the perimeter by adding up all of the sides of something here. So on the small end here, on the short end of perimeter, if we undermeasured, so let's see, we'll say short perimeter, all of these would drop. So the actual perimeter, if all of these were the correct height, would be 204 centimeters. But if we measured everything short here, that means this would be under half an inch, this would be under half an inch, under half an inch, under half an inch. And that would give us 2 times 23.5, because that's 24 minus 0.5. There's 2 of those. You could write out 223.5 if you wanted to. We'd say plus 2 times 77.5. And our short perimeter there, I'm just going to say SP, would be 202 centimeters. And so then our long perimeter here would be if we over measured every single one. We have to go with that assumption here. So we'd say 24.5 plus, or 24 plus a half is going to be 24.5 plus 2 times 78.5. That means our long perimeter is going to be 206 centimeters. And so the way that you can see that expressed more concisely, if you're listing the boundary values for its perimeter, if you look at the original perimeter, if that's what we assumed it would be, you need to think, what could I add and subtract to get both of these numbers? What could I add and subtract to 204 to get both of these numbers? And that's how you list your boundaries. We're going to say 204 plus or minus what value, and that would give us the boundary values for its perimeter. So you should be thinking to yourselves, well, 204 minus something will give me 2, plus something will give me 206. That number is 2. And so this right here, these boundary values, this represents the margin or the possible, if we're measuring, the possible parameters we could get from rounding here. The possible parameters we could get from rounding. And so we're going to look at a couple more of these just to kind of get the hang of it. So on this next one here, we're going to be looking at a paving brick that's measured 18 centimeters times 10 centimeters. And we want to know, what are the boundary values for its actual area? What is the smallest area we could get from this? What is the largest area we could get from this? So here's Mr. Price's brick. I'm obviously a gifted artist. Maybe we could put a little texture in there. Look at that. Look at that. So we've got 18 centimeters here by 10 centimeters. And we want to know what the possible things for our area are here. We want to know what the possible things for our area could be. So on the low end here, if we were off by so we're going to do the short area here. If we were off by a ½ inch, excuse me, ½ centimeter for both of these, then that would mean we'd be doing 9.5 times, remember you have to multiply for area, times 17.5. So the short area here would end up being 166.25. And then for the long area, we're assuming that we're a ½ centimeter long on both of those to get that range. So we'd say 10.5 times 18.5, and we would say, okay, that is, let me think. That's 194.25, and I guess I should put the units here. I really should. Centimeters squared. Now, with this area here, though, to get our middle boundary, what we're adding or subtracting to, we could say that the area is between this or this, but if we want to put it more concisely, we need to find the middle point of these two numbers. So I'm going to add these two things together real quick up here, just so I have a little bit of room. 0.25 divided by 2. That's going to give me 180.25. And then I'm going to look at this, and I'm going to look at both of these and say, what would I add to 180.25 to get 194.25? If I want to write this more concisely, I'm going to say 180.25 plus or minus, this is our error here, 14.25 centimeters squared. 14.25 centimeters squared here. And so with measurement error, you just have to be sure to add and subtract your half unit that could occur from error from rounding, and then find the short one, and then find the high one. So the last thing that we're going to do here, we're going to look at absolute and percentage error. And so whenever we measure a quantity, there's almost going to be a difference between our measurement and the actual value. We're human, we make mistakes, and we refer to this difference as an error. So the size of this error, whether it's high or low, we're going to refer to that in this class as the absolute error. And which sounds kind of scary, like absolute error. You're completely wrong. But it just means that it's just referencing the that we're going to take the absolute value of it. So if the actual or exact value, we're going to refer to that as V sub E, and the approximate value here is V sub A, we're going to calculate absolute error by doing V sub A minus V sub E. So we're going to do the absolute value of the approximate minus the expected. And if we want to express this as a percentage of the exact value, if we want to express this as a percentage, the way we calculate percentage error is the absolute value of V sub A, so the approximate minus the exact value, divided by the exact value, and then we're going to multiply that times 100% to convert it into one that's easy for us to work with. One that's easy for us to work with. And so when we're doing that, the actual formula for calculating that isn't too bad if you think about it intuitively. And so, again, I really just want to emphasize that we take a second. When you're doing these problems, think about what is it that I'm trying to find and how can I find it? Because a lot of these formulas are intuitive. If you'll take a second to think about, hey, what is it that this thing is finding? Does it make sense how it's finding it? If not, if you have a question on how it's doing it, please ask. And so we're going to apply this here in just a second. So what we're going to look at is an example. We're going to look at example 9 in your book there. And so what we're going to look at is Alan here wants to lay carpet on his 4.2 meter by 5.1 meter lounge room floor. He estimates the area of the lounge room by rounding each measurement to the meter. And so what we want to do is say, okay, we're going to put ourselves in Alan's shoes and see what happens when we estimate this thing right here. So Alan's estimate of the lounge room area, he's taken each of these things and rounding them to the nearest meter. So 4.2 rounded to the nearest meter is going to round to 4 meters. And then 5.1, so it's going to be 4 meters times 5 meters. So that's going to be 20 meters squared for the estimated area of his lounge room. So then the carpet here cost $39 per meter squared, per square meter. And we want to find the cost of this carpet using his estimate. So if it was 20 meters squared, think to yourselves, how would I calculate that if it's 39 per square meter? So all that we would have to do is say 20 times 39. And let's see, that's going to be 20 less than 20 times 40. So that's going to be 780. Or you could have just done 39 times 2. That would have been easier. So this is going to be $780. And what we're going to do is we're going to find the actual area of old Alan's, we're going to find the actual area here of old Alan's lounge room. So the actual here is 4.2 meters times 5.1 meters. And let's see, I'm going to need a calculator real quick. I can't do that one on the top of my head, so let me punch it in. That's going to give me 21.42 meters squared. 21.42 meters squared. And so what we want to do is we want to find the percentage error in Alan's estimation. So as a reminder, to do that, we're going to take the absolute value. We want the positive error in the approximate minus the exact. And then we're going to multiply that times 100. So Alan's approximate area here was 20. That's what he calculated there. So we're going to say 20. So the absolute value of 20 minus 21.42 over 21.42. And then we're going to multiply that times 100. So 20 minus 21.42, the absolute value of that is going to be 1.42 over 21.42 times 100. I'm not going to pretend like I know what that is off the top of my head. So let's see here. 1.42 divided by 21.42 times 100 to get it as a percentage. So he had an error. So here's the thing. Now where we are, now that we know in IB we have to round to 3 sig figs. First sig fig is 6. So we're going to go 6.2, and then 9's going to round that up. So we're going to call this 6.63%. We're going to apply what we know now. So for future reference, if you're rounding, we need to round to 3 sig figs. And the last question here is will Alan, is he going to have enough carpet to cover his lounge room? And this is kind of a little life lesson here. Alan's not going to have. He measured short by about 6% here for carpet in his room. So no, he won't. And let this be a life lesson to you. How should he have rounded the measurements? He should have rounded up. Because whenever you're doing any kind of physical labor job, it is way easier and way less annoying to go to the store once and get too much that you can always return than it is to get too little and then have to make another trip. Obviously, you all are 16, 17 years old, probably not doing a ton of home improvement projects, but just for future reference, if you're having to measure something for a physical job that you've got to do, I would always make sure to overestimate the amount of stuff you need. You can always return it as long as you haven't opened it. So that is kind of our short crash course on the unit of measurement. If you all have any questions, please let me know. Join my Zoom, shoot me an email, and we'll go over it. I was told that the hip thing to do is say smash that like button or smash the subscribe button. So do that. Get Mr. Price some clout, and we will go from there. But I hope you all have a good day, and if I don't see you, have a good weekend.